I am Harry Poston, Project Director of the American Statistical Association's project for the filming of distinguished statisticians. I am pleased to welcome you to the 14th Pfizer Colloquium of the Department of Statistics at the University of Connecticut. Since 1978, Pfizer Central Research has provided support for this colloquium series, and this has allowed us to bring to Connecticut the most important scientists in the field of statistics. It has also enabled us to videotape these colloquia for the archives of the American Statistical Association. We greatly appreciate the continued support of Pfizer Central Research. Now, to introduce our distinguished speaker, I will call upon my colleague, Professor Alan Sampson of the University of Pittsburgh.
It is my distinct pleasure to introduce this afternoon Professor Ingram Olkin. Professor Olkin is one of the luminaries of multivariate statistical research in the second half of this century and is also among the most effective and dynamic statesmen for statistics. His influential research spans the breadth of multivariate analysis, including estimation and distribution theory, probability inequalities, matrix analysis, majorization, and meta-analysis. Equal to his research impact has been his vision and energetic leadership in shaping our professional societies, our scholarly journals, national research policy, and the role of statistics in our universities. Professor Olkin is on the faculty of Stanford University, where since 1961, he has held the joint position as Professor of Statistics and Professor of Education. He received his PhD in mathematical statistics from the University of North Carolina in 1951, working with S.N. Roy and Harold Hotelling. He has been a visiting faculty member and scholar at numerous universities and institutes in both the United States and Europe. Among his many honors and awards are a Fulbright Fellowship, an ASA Founders Award, and in 1992 the prestigious Wilkes Medal. He was a major force in the founding of the Annals of Statistics, Statistical Science, and the Journal of Educational Statistics. He has served as president of the IMS, chair of COPS, and was a leading advocate for the establishment of the National Institute of Statistical Science. Also, Professor Olkin was the first chair of the Committee of Applied and Theoretical Statistics of the National Research Council. To try to summarize Professor Olkin's research is to attempt to encapsulate 5 books, 9 edited volumes, and more than 150 research papers written with more than 60 co-authors. His list of co-authors includes not only many of the who's who in statistics, but also co-authors who at the time were young statisticians whose careers were very much influenced by him. His first paper with Walter Deamer on Jacobians and multivariate analysis was published nearly 50 years ago, and these results remain in use today. One of his important early accomplishments was the development of the innovative multivariate exponential distribution. From Professor Olkin's lifelong interests in probabilistic and mathematical inequalities grew a long and fruitful collaboration with Al Marshall. This collaboration resulted in their book, Theory of Majorization and Its Applications, a book whose impact is often compared to that of Hardy, Littlewood, and Polya's classical text. Educational research has been a major stimulus to his statistical research. Nowhere is this more apparent than in his research for combining evidence across independently conducted studies. His early 1980s work with Larry Hedges in this area grew into Hedges and Olkin's 1985 book, Statistical Methods for Meta-Analysis. His continued groundbreaking research in meta-analysis has established him as one of the leading authorities on the statistics of meta-analysis. It is only appropriate that Professor Olkin speaks to us this afternoon on the topic, A History of Meta-Analysis.
Thank you. Thank you, Alan. Thank you, Harry. My topic today is meta-analysis, and I'd like to start with some definitions of meta-analysis, then discuss its history, give some examples, and finally discuss some of the statistical techniques that have been used. First, what is meta-analysis? Well, in 1989, Medline used the definition in their database. The definition was a quantitative method of combining the results of independent studies, usually drawn from the published literature, and synthesizing summaries and conclusions which may be used to evaluate therapeutic effectiveness, plan new studies with application chiefly in the areas of research and medicine. In 1994, the New York Times carried an article, and it had the following definition: a meta-analysis aims at gleaning more information from existing data by pooling the results of many smaller studies and applying one or more statistical techniques. The benefits or hazards that might not be detected in small studies can be found in a meta-analysis that uses data from thousands of patients. Thus, in some sense, meta-analysis encompasses the process of combining results from independent studies. Historically, the teaching of statistics has focused on a single experiment, which we might call a primary analysis. Every statistics text provides numerous such examples. Let me quote the results of one such study. A study of 237 individuals showed a positive correlation between coffee drinking and pancreatic cancer. This study raised questions about its validity. The individual patient data was made available, and a reanalysis, which we in general might call a secondary analysis, showed that 82 patients had a history of gastrointestinal problems, which contaminated the results. Of the remaining 155 patients, there was no indication of a correlation between coffee drinking and pancreatic cancer. Now, in general, there are not too many secondary analyses, and mainly because original data is seldom available. It may be costly to remove identifiers and to clean the database for someone else to use. And also, there's a reluctance on the part of researchers to release their data. The Food and Drug Administration, the FDA, has access to original data, and they do carry out many secondary analyses. So we come to a hierarchy. We have a primary analysis, possibly a secondary analysis, and now we come to the point of combining results from independent studies. The term meta-analysis was coined by an educational psychologist, Gene Glass, in 1976. He was interested in assessing the effect of class size on achievement. However, the idea of combining information goes back a long time. One of the earliest examples is that of Carl Pearson. In 1904, he combined the results of 5 studies on the effects of an inoculation on enteric fever. He had data from India and Africa, but he used only the data from India for combining. But it was really R.A. Fisher. In statistics, the grandparent of almost all methodology is R.A. Fisher, and here again his name comes up. He was the first to state the problem in a general way and to provide a statistical procedure. In the 1932 edition of his book, he writes the following: when a number of quite different independent tests of significance have been made, it sometimes happens that although few or none can be claimed individually as significant, yet the aggregate gives an impression that the probabilities are on the whole lower than would often have been obtained by chance. It is sometimes desired, taking account only of these probabilities, not of their detailed composition, of the data from which they are derived, which may be of very different kinds, to obtain a single test of significance of the aggregate. Fisher's method is based on the product of p-values. Now, his interest in combining results arose from an agricultural context. However, motivated by industrial applications, L.H.C. Tippett in 1931 proposed an alternative method based on the minimum of p-values. Somewhat later, in a major series of studies in social psychology following World War II, Samuel Stauffer, a sociological statistician, in 1949 proposed yet another method in which each p-value is converted to a normal score. This method was stated in a footnote that could easily be missed. It was later explained explicitly in a paper by Fred Mosteller and Robert Bush in 1954, who discussed other methods as well. These three methods, the Fisher, the Tippett, the Stauffer, are based on the chi-square distribution, the uniform distribution, and the normal distributions. And they comprise the standard methods for the analysis of p-values. Now, other discussions are provided in the book that Alan referred to, written jointly with Larry Hedges, and also extensively studied by Betsy Becker in a dissertation. So Fisher's work was about 1932. In 1950, Egon Pearson wrote a paper in which he wrote the following: in statistical practice, it often happens that we wish to continue the results, to combine the results of a number of independent experiments which have all been planned to test a common hypothesis. Thus, for example, several experiments comparing two treatments may have been carried out, but owing to differences in error variance or to other changes in conditions between experiments, it is not possible to pool all the data together. The overall test calls, therefore, for the combination of a number of independent tests of significance. That was 1950. In a psychological context, McNamara and Terman in 1936 had collected data on an intelligence test given to 13 similarly selected samples of boys and girls of age 13 to 17 in various cities. Gordon, Loveland, and Curitin in 1952 used this example to combine results using Fisher's method. The introduction to their paper is a reiteration of the need for combining results. Duplicate studies and studies bearing on the same essential problem, but based on samples from non-identical populations, often lead to tests of significance whose associated probabilities are quite unequal. If each sample is small, moreover, the null hypothesis may not be rejected with any great certainty on the basis of any one study. But if the results of the several studies are all or nearly all in the same direction, there is additional evidence against the null hypothesis. In such cases, we may wish to base a new test of significance on the combined data from all the studies. Now, so the history is approximately 1930, 1950. There were a number of papers during the 1930s by Cochrane, and these were motivated by agriculture. Now, there was not much research on meta-analysis from 1950 to 1976. And as I mentioned, Gene Glass's work in 1976 really rekindled the field of meta-analysis. During the last 10 years, there's been an explosion of meta-analytic studies. One question is why? I believe that one part of the reason is that the research community is overwhelmed by the amount of scientific information being published. The current estimate is that there are at least 40,000 journals now being published yearly, with more than 1 million new articles per year, much of which goes unread. It's very interesting to note the following figures. In 1940, there were 2,300 biomedical journals. There are now over 25,000. That's a factor of 10-12. The number of psychology journals has risen from 90 to over 1,200 in this period, and the mathematical science journals has risen from 90 to over 1,000. The number of articles in mathematical sciences has increased from about 3,500 in 1940 to considerably over 60,000 now. So, how can we deal with this information explosion? In some fields, meta-analysis may provide a partial answer. A search of meta-analysis articles in medicine for the year 1996 uncovered 230 meta-analyses of randomized clinical trials and about 75 on non-randomized clinical trials. The specific areas included 26 meta-analyses in cardiovascular diseases, 32 meta-analyses in oncology, 28 in psychological techniques, and at least one in almost every medical field. During World War II, I was a meteorologist in the Army Air Force, and for somewhat nostalgic reasons, I periodically look at meteorological journals. I found the following two quotes about cloud seeding, which shows some of the problems which are very similar to medicine. This one is from the Journal of Weather Modification, and it's by Clement Todd in 1986. Relating different cloud seeding responses to cloud types and characteristics in an organized way has shown a physical basis for sound technology. The problem is that few projects include enough similar clouds to achieve statistical significance within themselves. It is necessary then to assemble information from a large number of projects to demonstrate that there is a broadly based technology. In another quote from the same article, some people are hoping for the day when an elegantly designed experiment, brilliantly evaluated, will make precipitation management credible to those who look at the field from the outside. But it doesn't appear as though credibility will come that way. Rather, it will come from reporting on information assembled from a large number of imperfect experiments and operations that show, even though there is diversity in the way different clouds respond to seeding, similar clouds respond similarly around the world. Now let me turn to some of the aspects of meta-analysis. Several important decisions need to be made early when trying to do a meta-analysis. Point A, how do we choose the data that is to be combined? Obviously, if we choose journals that do not comprise a randomly selected subset of articles, then we will introduce a bias. So one question is whether we have a complete database of articles. Foreign language articles are an issue. Do patients in Asia, for example, react the same as those in the United States? B, coupled with obtaining an exhaustive group of articles, there's a basic question of whether there is a preponderance of papers that show significant results. That is, are we observing only papers that show significance? And do there exist unpublished papers that show non-significance? This is a problem that has been called publication bias. C, are patients selected representative of the population to which we wish to generalize? A well-known example is that of the aspirin study, in which this study was on the occurrence of heart attacks. The study consisted of men doctors. So the question is, should we generalize to all men? Should we generalize to women? Does age constitute one of the questions? Different studies will generally have different outcome measures. Even in a dichotomous response, such as whether the patient had a stroke, there may be different times of occurrence, different ways to measure stroke, and so on. This is compounded when different therapies are used for the same problem, such as different therapies for acute heart attacks. Here the word acute may be determined differently. Thus, there's a problem of what measures to combine and what statistical procedures to use to do the combining. Now, although these problems may have a non-statistical component, statisticians have created models to try to resolve some of these problems. I'd like to illustrate with one such model that I happen to be involved in. As I mentioned a while ago, one concern in meta-analysis is that there may be unpublished studies that could affect the outcome. This problem has been called the file draw problem, in the sense that there are unpublished studies that show non-significance that are lying in file draws. Now, there may be other reasons for the file draw problem. For example, some studies are supported by companies who have proprietary reasons for not publishing. Robert Rosenthal, a social psychologist at Harvard, devised a measure of the seriousness of this problem, and he called it the fail-safe number. The fail-safe number is the number of studies showing non-significance that it would require to overturn the result. The idea is that if the fail-safe number is not large in comparison with the number of published studies in the meta-analysis, then we would not be concerned with the answer. The specific computation is based on assigning an unknown number n, capital N, of p-values equal to a half, so that the overall p-value is above the alpha level of 0.01 or 0.05. The computation is on this first transparency. The sum from 1 to k is the sum of studies of the p-values that we actually observe. On the other hand, there are n studies that we don't observe. Now, this sum has a chi-square distribution with 2k plus 2n degrees of freedom. So we can now set that equal to, say, 0.06, which just is above the 0.05 level, and then thereby be able to determine the value of n that would overturn the result. Actually, Rosenthal used an equivalent formulation in terms of the normal distribution, and I've written it in terms of the chi-square distribution. Now, one failing in the fail-safe number is that it's model-free, and it doesn't lead to probabilistic statements. In a 1996 paper that appeared in Statistics in Medicine, Leon Glaser and I proposed a model that provides an estimate of the number of unpublished studies. I should note that a number of other people have discussed this problem. Rosenthal in particular, Iyengar and Greenhouse, Bayari and de Groot, Begg and Berlin, among others. Now, the idea here is as follows. Suppose that we observe k reported studies from a totality of capital N plus k studies. N is unknown. So now let us assume, as a first approximation, that the N plus k studies, both reported and unreported, are mutually statistically independent, but that the p-value in each study is based on a continuous test statistic, with the simplest assumption that the studies observed have the smallest p-values. We can write down the joint distribution under the null hypothesis. And that is what you observe on the first line, namely the joint distribution is n plus k factorial over n factorial times 1 minus the largest p-value observed to the nth power. Now, from this, once we know the joint distribution, we can then show that the maximum likelihood estimator of the unknown n is given by the greatest integer in k times 1 minus pk over pk. So we actually get the maximum likelihood estimator. You can also get an unbiased estimator, and that's not hard to do, and it's very close to the maximum likelihood estimator. There's a factor of -1. In this model, what we have assumed is that we've observed the k smallest p-values. Now, that may be unrealistic. A more realistic model is that we observe m less than k smallest p-values, and the remaining k minus m observed p-values are sampled at random from the n plus k minus m largest p-values. And again, it's a slightly more sophisticated model, but again, we can obtain maximum likelihood estimators of the number of unpublished studies, and we can also get a confidence interval. I think it's important to note that the beauty of this process is that what meta-analysis has permitted us to do is get a problem, understand an application from which the statisticians have come up with a procedure that we would not have thought of doing prior. This is definitely meta-analytic oriented rather than a problem we thought of at home. Now, meta-analysis is based on quantification, and there have been a number of synonyms for meta-analysis, such as overview, synthesis, amalgamation, combining, pooling, and so on. However, the key ingredient that meta-analysis has that the other words do not have is a quantification. And once I say quantification, then the statisticians have different types of quantification. So, some have used significance levels. Some have used standardized mean differences. Some have used proportions, regressions, ANOVA, correlations, and Bayes procedures. And of course, there are others. Historically, p-values were used in a variety of contexts. However, p-values serve as a first-order estimate of an effect. They serve as useful diagnostic tools, but do not serve well for estimating effect sizes. Now, different types of data dictate the types of analyses to be used. So let's talk for a moment about the types of data that arise in applications of meta-analysis. There are really three fundamental types. The first is where we have two normal populations with respective treatment means, mu t, and variances sigma squared t, and control means mu sub c and variance sigma square c. The effect size is the standardized mean difference, which I'll call delta, which is the difference mu t minus mu c normalized by a standard deviation. Now, if the population variances are equal, then we might have a common sigma. If they're unequal, people usually take the control standard deviation. The second type of data are 2x2 tables, in which pi t and pi c are the treatment and control population proportions of dying, which are estimated by sample proportions. Now, the measures of discrepancy between treatment and control are either proportion differences, proportion ratios, odds ratios, and so on. And then the third type is where we have two bivariate normal populations, where now the effect size is a measure of the difference, say, between the correlations. So we have the three different types of data. In one, people use standardized mean differences. In others, they use some kind of difference of proportions, odds ratios, and so on. And in the third, they use correlations. I'd like to focus a little bit on a discussion of the first type, namely the standardized mean difference. Here we have sample estimates, we have sample means and sample variances, and let's call D the mean difference of the treatment and control standardized as an estimate of the unknown population delta. The distribution of D, except for constants, is that of a non-central t-distribution with non-centrality parameter delta. So once you know the distribution, you can obtain and compare maximum likelihood estimates, unbiased estimates, shrunken estimates, and so on. However, for large samples, all of these estimates are approximately equivalent. The factors that make for the difference generally approach 1 as the sample size increases. So given k different studies, we can test for homogeneity of effect sizes, delta 1 up to delta k, and if satisfied, we can then use a linear combined estimator to estimate the common effect size. So here, D plus, as on the second transparency, D plus is the weighted sum of the weighted average of all the effect sizes from the case studies. Now, as you might expect, the weights are proportional to the inverse of the variances, and the weights are given there in the second line. The main point is to obtain the asymptotic variance, and this is estimated by sigma hat squared, which is equal to nt plus nc over the product, plus d squared divided by 2 nt plus nc minus 2. This asymptotic variance is what we would call unstable, and so one can actually obtain a variance stabilizing transformation. And I'm not going to discuss that at the moment. Now, the accuracy of the large sample normal approximation to the distribution of the D's suggests that the approximation to the distribution of D plus will be reasonably accurate in many situations. We should expect D plus to have a slight negative bias for positive delta because fluctuations in the estimators are negatively correlated with fluctuations in the estimated weights. This is because larger values of the DI lead to smaller values of the WDI, and smaller values of DI lead to larger values of the WI. Consequently, when delta is positive, large values of the D's are underweighted, and small values of the D's are overweighted in the calculation of D plus. Now, simulation results suggest that large sample approximation to the distribution of the estimators is reasonably accurate for the range of delta examined, even when all the studies have a sample size of 10 per group, which is quite small. Now, a not uncommon situation is where each study is a comparison of more than one treatment versus a control. Furthermore, each study need not have all the treatments. The next schematic shows an example of such a design. What we see here are, in this example, are 3 studies in which there's a single control, and then we have a number of different treatments. We have penicillin, erythromycin, tetracycline, streptomycin, and so on. The key point to note is that not each study has each of the treatments. So the statistical problem that arises is that the effect size for each treatment contains a common control. Thereby, if you compare penicillin with the control and then compare tetracycline with the control is common to both, and so the estimates are correlated. One has to take account of this correlational effect. Leon Glaser and I have proposed a solution as follows. To fix notation, suppose that there are case studies, that each study with p potential treatments. The effect size estimates for the p treatments in any single study are the standardized mean differences. So now we have a mean of the treatment for each of the treatment effects, and we have a common control, y bar 0, and a standard deviation. An estimate of the asymptotic variance of the D's and the asymptotic covariance of the D's needs to be calculated, and the asymptotic variance is given by 1 over the sample size for that particular treatment, plus 1 plus a half dj squared over the sample size of the control. And the covariance is similarly noted. Now, we embed this model into a regression format. D is x beta plus epsilon. And now X is the design matrix that takes into account the missing treatments. And that's the key point here. The betas denote the effect sizes. So now we can do a least squares analysis. This is not ordinary least squares, but it's weighted least squares. And what it does is yield an estimate where now you see that psi hat is the estimated covariance matrix. So we obtain beta hat. We know its estimated covariance matrix. That's x prime psi hat inverse x, that inverse. And so we can actually obtain simultaneous confidence intervals for linear combinations of the betas. We can also do a goodness of fit test that the regression model fits. And that's based on the statistic Q, which is fundamentally computed by looking at the D's, the asymptotic covariance matrix estimates, and the beta hats. This Q has a chi-squared distribution with degrees of freedom equal to F, the dimensionality of D, minus Q, the number of treatments. Once again, I'd like to point out that this whole statistical analysis arose from a practical application in which an actual set of studies noted that they had this single control and different treatments. And this has arisen over and over again. I'd like to talk now about some diagnostic procedures. The issue of how many observations can be set aside without compromising the statistical analysis is clearly a difficult one with no obvious solution. Now, this arises in meta-analysis over and over again because some of the studies may have patients that are quite different from the patients in the majority of other studies. Now, there's considerable evidence that real data contain occasional observations that do not fit simple models well. The early developers of statistical methodology certainly believed that the exclusion of a certain amount of data from statistical analysis solely on the basis of deviant values was a good practice. Legendre, who is credited with the invention of the important statistical idea of least squares, recommended in 1805 the use of his method after rejecting all observations whose errors, quote, are found to be such that one judges them to be too large to be admissible. whatever that means. Edgeworth, in 1887, another important contributor to the foundations of data analysis, reached the same conclusion. I quote, "The method of least squares is seen to be our best course when we have thrown overboard a certain portion of our data, a sort of sacrifice which has been often made by those who sail upon the stormy seas of probability." Modern exploratory data analysts generally agree that it is usually necessary to eliminate a few data points from any set of data in order to describe the data by a reasonably simple model, as noted by John Tukey in 1977. How much data needs to be sacrificed to obtain a reasonable fit to a model is regarded by all as a difficult question. Steve Stigler, in 1977, examined several historical data sets in the physical sciences, and he concluded that, quote, "Outliers are present in small quantities, but a small amount of trimming, no more than 10%, may be the best way of dealing with them," end quote. Stigler's 10% trimming actually means discarding 10% of the highest observations and 10% of the lowest observations. So his recommendation amounts to discarding not more than 20% of the total observations. Whenever data are deleted solely to improve the fit of a model, we should determine whether the deletion of the data changes other conclusions besides the assessment of goodness of fit of the model. If the deletion of a few observations improves the fit of a simple model, but does not greatly affect the overall mean, for example, then such a deletion is probably well justified. There are a number of ways that we can employ diagnostics. I will discuss one method that was developed jointly with a student of mine, Hilary Sainer, in her dissertation. Now, Fisher enunciated without proof a method based on the product of the p-values that I've mentioned. Under the null hypothesis, each p-value is uniformly distributed, so that minus twice log p has a chi-square distribution with 2 degrees of freedom. And hence minus 2, the sum of the log pi, has a chi-square distribution with 2k degrees of freedom. Alan Wallace in 1942 gives a very nice geometrical derivation of Fisher's method. Now, if we wish to weight each study by some measure of importance or quality, then we would have a weighted sum of exponential random variables, a statistic that has arisen in other contexts and has received considerable study. When we analyze the results of k independent studies, we may wish to be conservative in our conclusions. Now, one conservative approach is to trim some of the most significant p-values and to analyze the remainder. Following Fisher's method, we now have a sum of ordered p-values. So we're not taking the sum of all the p-values, but just the ordered ones, and deleting the bottom most significant ones. Consequently, the distribution of the ordered p-values will no longer be chi-squared, because each order statistic can be represented as a sum of spacings, and the normalized spacings of exponential random variables are independent and identically distributed. We have reduced the problem to one in which we have a sum of weighted exponential variables. Now, we've now reduced the problem to that of a linear combination of exponential random variables, and there's a considerable literature on that. Other diagnostic procedures that one might use are the following. We might repeat the analysis, omitting one study at a time. This helps detect particularly influential studies. In what you see on the board, this is a set of 5 studies in which one study was deleted at a time. And so each of the analyses, each of the confidence intervals and the point estimate is based on 4 studies, except the bottom one, which is based on all. And what you see here is that although there's some variability in the confidence intervals and the point estimates, none of the single studies is particularly influential. So one of the themes is to make sure that there's consistency between the studies. We could carry out alternative methods of analysis for consistency of results. One does not want the result that a treatment is effective or not effective to depend on whether we're using a frequentist method, a Bayesian method, a non-parametric method, a time series method, and so on. We would like all of these to corroborate one another. We really need to carry out simulations with small perturbations of the data. This is particularly important when you have small cell counts in 2x2 tables. And so the recommendation that I would make is that you perturb the data by adding or subtracting one observation, one value in each of the cells, especially the cells with small numbers, to make sure that the answers do not depend on one small value. One might term this the fragility of proportions. Proportions are indeed very fragile. Although a half is equal to 10/20ths, is equal to 100 over 200, a half is a fragile proportion. 10 over 20 is more robust, and 100 over 200 is quite robust. And the point is that an additional observation will change a half to a third or 2/3, but 100 over 200, when you add the next observation, just changes it to 100 over 201 or 101 over 201. Very little change. One issue that arises in meta-analysis is whether one should use literature summary data or whether one should use individual patient data. For simplicity, I refer to these as MAL, M-A-L, for meta-analysis of literature data, and MAP, meta-analysis of patient data. Now, there are advantages to each. In a study on oral contraceptive use and ovarian cancer, which I was involved in jointly with members of the Centers for Disease Control and Prevention, we reached the following conclusions. A meta-analysis from literature can incorporate studies for which individual patient data is unavailable. Because individual patient data is hard to obtain, this is an important point. A meta-analysis of patient data can scan for subgroup analyses that may not be available in summary data. A meta-analysis of patient data is considerably more costly and time-consuming than a meta-analysis of literature data. In fact, we found a 10-fold cost factor from $250,000 to $25,000 in making our comparison. A meta-analysis of individual patient data can use a logistic regression, which is generally unavailable with summary data. The next point is an interesting statistical issue. Namely, will an analysis of variance of individual patient data in which study is one factor yield similar results to a meta-analysis of summary data? In a recent joint paper, actually with Alan Sampson, we show that the results we obtain are identical. Although this fact may appear to be intuitive, the proof is elusive. The reason is that with an unbalanced analysis of variance, there's no closed-form solution to the normal equations. Consequently, we did not find any direct way to show that the results were identical. However, by showing that there is a unique solution with a certain variance and then exhibiting that we achieve this variance by the other method, the two solutions must be the same. A surprising byproduct of this finding is that the meta-analytic solution provides a nice, manageable solution to the analysis. Prior to the introduction of inferential procedures, there were a variety of ad hoc methods. One such is what became known as vote counting. Vote counting is the kind of procedure where you look at the proportion of significant results or the proportion of positive results. And then subsequently, you might try to do a sign test to see whether the true proportion is a half. Although vote counting methods have a general appeal, they do not provide estimates of effect size. Larry Hedges and I have shown that under certain conditions, the vote counting method may tend to make the wrong decision more often as the amount of evidence, namely the number of studies, increases. This was a very surprising result, because usually one expects that as you gain evidence, as you get more and more observations, that your method will be robust and converge to what it's supposed to. This result is very surprising. On an intuitive level, the hypothesis test in each study has a chance of yielding an incorrect decision. In this case, the effect is non-zero, and the incorrect decision is failing to detect a real non-zero effect, a type 2 error. Because the possible errors are of the same type, they do not cancel out one another. In fact, as the number of studies becomes large, the proportion of studies yielding significant results is approximately the average power of the test. It behooves us to mention that expert panels have often been used to determine whether a treatment is efficacious. In recent years, expert panels have been used to determine the effects of acid rain, whether there is a connection between alcohol use and cancer. And most recently, people may be aware of the fact that it was an expert panel that looked at the use of mammograms as a screening device for breast cancer. Panels have to calibrate their responses so that each person will use the same scale. In the acid rain study, this was accomplished by creating a star system of 0, 1, 2, or 3 stars, 4 stars. Thus, for example, 0 is no basis for an answer, 1 is a limited information is available, up to 4 stars, substantial amount of information. The conclusion from panels is perhaps exemplified by the following conclusion from an alcohol breast cancer panel. A significant positive association between alcohol intake and breast cancer incidence was seen in each of 4 large prospective studies and in 7 of 13 case control studies. In 2 of the case control studies, with a limited number of subjects, positive associations of similar magnitude were observed. A dose-response relationship, generally up to 1.5 to 2-fold risks, has been observed. The consistency of this positive association makes it unlikely that the relationship is due to chance or methodological bias. This description, though partially quantitative, is more of a qualitative synthesis. It does not provide probabilistic assessments in the form of confidence intervals or posterior distributions, for example. Well, I've tried to indicate the statistical and non-statistical ideas behind meta-analysis. Perhaps more important is to note the richness of applications. Nature presents a plethora of statistical problems that it would be hard to think of without the needs of the application in hand. Nature will guarantee that there are always interesting statistical problems to solve. Thank you.
Thank you, Professor Olkin, for a good survey of meta-analysis. This concludes our 14th Pfizer Colloquium.